Namaste. In this video we are going to see NFAs accept the regular languages in detail. Equivalence of machines. Definition: machine M1 is equivalent to machine M2 if language accepted by M1 is equal to language accepted by M2. So here M1 and M2 will consider M1 as DFA and M2 as NFA, or M1 as NFA and M2 as DFA. We'll see how they are going to be equal, or by definition actually they are equal. We'll see one example for proving this definition. So before that, we'll see the construction of the automata for the given language. For example, let us consider the language 10 to the power closure. How we can construct this automata for this? How I can construct NFA is that because it is a star closure, my initial state should be the final state. Next, it will accept 10 any number of times. So this is a final state. Then 10 any number of times. Here I have two symbols 1 and 0. So Q0 on 1 I have a transition. On 0 I don't have transition. And also Q1 if I say on 0 I have a transition, but on 1 I don't have the transition. So it is a NFA. We'll see how to construct the DFA for this same language. So I have to write the same thing. Q0 on reading 1 0. So the same thing remains, but Q0 on 0 I should not have a transition for this language. So that is going to the trap state, and Q1 on reading 0 I have a transition. In case if it reads 1, again it has to go to the trap state. And after going to the trap state, even this is also a state, it should also have the transition for 0 and 1. So it is a self loop. After going to the trap states, any number of zeros and ones we can read, but it remains in the trap state. So for this is the language where I can construct both the NFA and also the DFA for the same language. So I can say both the machines are equivalent and also both are equally powerful. We will prove language accepted by NFA is equal to regular languages. Languages accepted by the finite automata. They will have the computation power. So the languages accepted by deterministic automata will be a regular language. And the languages accepted by the push-down automata, we have already seen it is context-free language. And the language accepted by the Turing machine is that recursive languages and recursively enumerable languages will be accepted by Turing machine. So these three types of automata we have seen in video 1. But the languages I have discussed now. Okay, we'll see that in detail in Chomsky's hierarchy later. So here I can say both as a languages accepted by NFAs, a subset of a regular language, or regular language is a subset otherwise. So we will show we'll see this. So proof for the first one. Every finite automata is finite automata here. It is a deterministic automata is trivially and non-deterministic finite automata. Any language L accepted by a deterministic automata is also accepted by non-deterministic finite automata, and also any non-deterministic automata can be converted to an equivalent finite automata. So any language L accepted by an NFA is also accepted by finite automata. So now what we are going to see is the conversion of the one automata to other automata. So how I can convert the given NFA to the finite automata we are going to see. So what is your, in this is the given NFA which is having epsilon transition. How we are going to convert this NFA to finite automata we are going to see. Initial state is Q0, you have to keep Q0 as such. Next, Q0 on reading A, what is the transition I have to see? Q0 on reading A, I have transition to Q1 and also to Q2 and also to Q2. So the next state, so this is the finite deterministic finite automata what I am constructing. So initial state will be same. So what I have to do is on reading A, I will be in Q1 and Q2. That both the thing I have to consider as a single state. Next, Q0 on reading B, do I have a transition? No. So it will go to a trap state. Next, what I have to see is Q1 on reading A, what is the transition? Q1 on reading A, I have transition towards itself. And on epsilon transition, it is going to Q2. So this I have to consider as a single state. So Q1 on reading A, it remains in the same state. Next, Q2 on reading B, it is moving to Q0. So I have to add the transition for Q0. And how to consider the final state? So in this, Q1 is final state. So wherever I have Q1, I have to make that as a final state. And Q2, if I see, dead state will be trap state. A and B I have to add. And Q1, Q2 will become the final state. So here, the language accepted by this automata is similar to the language accepted by this automata. So that proof we have seen now. Now we'll see NFA to finite automata conversion. We are given an NFAM. We want to convert it to an equivalent deterministic finite automata with language or equal. What we need to construct is finite automata. Finite automata definitions we have already seen. Set of finite states, input alphabet, transition function, initial state, and set of accepting states. If the NFA has states Q0, Q1, Q2, the finite automata has states in the power set. So in the NFA, if I have any number of states, how many maximum possible states I can have in deterministic finite automata is nothing but the power set of the given set. So initial state procedure for the conversion. Initial state will be Q0, the same state. Next, what we are doing is compute the transition for each states. This is what we have constructed. Repeat step 2 for all letters in alphabet until no more transitions can be added. So NFA, is it done? No. This step it is not done because I have to construct the final state. For any finite deterministic finite state, if Qj is accepting state in FA, then Qi, Qj and Qm is accepting state in deterministic finite automata. That is, I can have any number of states, but I can have the subsets in that if one of the value is the final state, then those states will become the final state. So this is what we have discussed already. Next, single accepting state for NFAs. So how any NFA can be converted to an equivalent NFA with a single accepting state. How we can do that, we'll see. Here if I see, I have two final states. This one is also a final state. This one is also a final state. How I can do is that I can consider one single final state. What I can do is from this final state to that final state, I can have a epsilon transition, and also from this state to the final state, I can have a epsilon transition. So this is the idea. So in general, NFA will be having multiple final states. In that case, how I can do is, I can have a lambda transition attached with that. We'll see the rest contents in the next video. Thank you.